All right. Thank you, Alison, for the wonderful introduction. So I think it's a great honor to have an opportunity to speak to you about this plasma-assisted combustion and electrified manufacturing. I think that, as I said, a lot of people, I say, if we go to combustion symposium or meetings, people are always asking together, what is that the future of combustion? But I think that the knowledge we gain in combustion, especially in that the transport and that the kinetics, and will be applied to many areas and towards the future. So what I'm going to do today, and probably try to introduce you one of the specific area that is the plasma-assisted combustion and electrified manufacturing. What do you want to see that actually these plasma and electrified manufacturing, the process is exactly similar to the combustion we are studying, but open a much bigger world and to research and technology development. So what I try to say in the beginning, to say the people who worked with me in plasma-assisted combustion, Tim Marambello, right now is the Air Force Research Laboratory, Wen-Tin Sung, Georgia Tech, Jordan Kovitz, and Israel Institute. Eric Rosso is the manager at Lawrence Livermore. And then Tim Chen applies materials, and Madeline working for Fusion and a company, and visiting professors. And he just left for China to take a position in Tianjin University. And he got a faculty position, and starting from July, Michigan State University. And he took a position from Hong Kong. And Andy, you know, he's here. He will take a professor position, and EJ is a graduate student. So over the years, I collaborated with a lot of people, and other than in combustion areas, like diagnostics, Andre and plasma. Chris and Igor, they are plasma people. Svetlana is plasma. Liang Binghu is a professor moving to Yale. He's a manufacturing guy. And these two you know is Niels Hansen at the Sandia, Chris Cleaver, Diagnostics. Anime Burgess, one of the most active person in plasma research and University Antwerp. And Professor Char and Michael Schneider on different areas. So when you try to collaborate with people in different fields, and you feel that it is so exciting to stimulate many ideas that are different from what you have in that your original field. So what I'm going to talk today are a few things that because too many people, that plasma is something probably new. To some of you, you have probably are already expert in the plasma area. But don't worry, so I try to give you an introduction, what is plasma, and after you listen to it, and you will feel like, wow, plasma is just like a flame or just like a combustion. They have ignition front, they have a propagation speed, and they have instability, and they have chemistry. So that is what I try to share with you today through that a few introduction of plasma physics and discharge. And once you understand this, and it's very hard. Plasma is very difficult to get into it because the bar, combustion, to learning combustion, the bar is very high. You have to understand fluid mechanics. You have to understand chemical kinetics. You have to understand heat transfer, and then mathematics. So, but plasma is also very high bar. You have to understand physics. You have to understand electrons and non-equilibrium. And you have to understand that the Boltzmann equations. So it's a very high bar. Combine them together is just so difficult. But when you are young, it's a great opportunity and to take some challenge in the fall. And then I show you some examples of the plasma, how do they change combustion in engines and in laboratory. And then try to show you some fundamental phenomena about ignition, flame propagation, minimum ignition energy, and the cool flames. Then we start talking about that how electric field will affect that the flame stabilization, and how plasma chemistry and kinetics they couple with combustion. They enhance combustion process. And we try to do what are the laser diagnostic approach for plasma and how that the plasma and combustion, they couple together, they drive a different instability and in a reactive flow. Then we talk about how do we model it, and then, then lastly, and probably most exciting, is that how plasma can help manufacturing for in future research. So, and if I have time, I will talk about this. If I don't, I will probably skip of this. Try to give you some kind of review papers that this is the area that is growing. If you go to Department of Energy conference, you find that the Oak Ridge National Lab, you find that the Sandia, you find the Princeton Plasma Physics Laboratory, National Renewable Research Laboratory, they're all doing plasma suddenly. And because why? The clear reason is electrified processing in the future, right? So there are some, Andrea and I are writing a book by CEFRC, and hopefully will be published in next March. And there are a bunch of, for combustion people, you can read some of the earlier work about mine. And then you have Igor Starkovskaya, Chris Locks. And these are the combustion people. For physicists, Race, Gaseous Charge is one of the best books. And Michael Schneider. So these are the two books for physics of plasma discharge. And for modeling, you can look at the Anime Bogus and the popular paper of plasma catalysis and the roadmap. And recently that Lacoste, and they give a review of talking about plasma with flames. So these are listed in your document. You can look into it, and then you figure out what that you like to do. So why plasma these days? Why electrified manufacturing? So every time that when you have a innovation, and for example, internal combustion engine, or find that fossil fuel, and you ignite that a new industry and business, which is that combustion, and then chemical engineering. But the consequence of this process from fossil fuel, and that created that a lot of a carbon footprint. That become a great impact in climate change. I don't want to elaborate too much about that. But today that you got people using biomass, using photosynthesis, photochemical synthesis, and they wanted to derive a biomass and then try to do a green combustion or green fuel. But unfortunately, this process is very inefficient. This whole process probably just about 1 or 2% of efficiency, depending on what kind of crops you want to do, and require a lot of land, a lot of water, and a lot of processing. But if you think about the renewable electricity from nuclear and also from wind and solar, and they're higher than 25% of efficiency, and is order of magnitude efficient about this. So this will be another industry revolution that is driving new research areas, driving new industry. So what are the new industry? First, you have to store this energy because they are intermittent. So therefore, battery becomes one of the major hot potato in the last few years, and in turn for energy storage. And if you have enough electricity, and then you can, like Germany, sometimes the electricity become so large that nobody can use it. So you have a negative electricity price. That time, you can do chemical synthesis and catalysis to make new fuels that will decarbonizing the transportation process. And so therefore, I would say that the time comes from fossil fuel energy to electron energy. So energy will be a form in the electrons. The question is, how do you use electrons? You can using lasers to do photosynthesis. You can using electrochemical systems for battery, for chemical conversion. You can also using electroheating, just to heat it. And you may say heat is boring, but that's not true, because heating, it can ramp it up much faster and than combustion process. And that can manipulate the reaction. You cannot do it with combustion. They can control the temperature very, very well and in a broad range than combustion. So I think that And then you can also do it in a plasma, that coupling that the electron energy and with that the reaction, to do some research that you never done before. So I try to impress you with one thing, that the Department of Energy that funded 11 energy Earthshot Center. And they spent $200 million to do that. This is one of the major research effort in Department of Energy in parallel to Energy Frontier Research Center. Energy Frontier Research Center, we had it in combustion more than 15 years ago. So that is really the basic research of but this one not only is basic research, but also they want you to have impact. And that is the difference. If you're looking at the title about from the first one is that the wind, and second one is that the steel manufacturing using electrosynthesis. This is the plasma, and this is the non-equilibrium transfer. And this is that the offshore modeling, this is modeling simulation. This is the reaction. So if you're looking at this, most of them, 7 out of 11, they are reactive flow. They may not be combustion, but they are reactive flow. You have to not understand what is flow, what is that but most of it are electrified process. See what I'm saying? So this is why that the electrified process become a very popular, not only in combustion area, but also in chemical engineering, in material synthesis, in many areas, and because of that the green energy. So what I'm going to do to start that he's talking about is some kind of plasma physics about the chart. Be patient, because this is different from combustion. It took me several years to learn, and once you finish your PhD, you want to get into a new field. It's very challenging, because you have to compete with the people in the other field, and you feel not welcome unless you bring something new, right? So, but don't be afraid to do that, so this is once you have combustion knowledge, it's quite easy to understand plasma and then the reactions. So first, what is plasma and how plasma is relevant to combustion? And what are their applications? So I try to give you some basic thinking about what is plasma. And then we're talking about the plasma properties. Just like combustion property, you have ignition, flame speed, minimum ignition energy, and flammability limit, a lot of things. In plasma, they also have their language about that. What is breakdown? It's just like ignition. And then what is that the plasma regime? For example, in combustion, we have cool flame, high temperature flame. In plasma, you have the glow discharge, you have arc, you have dielectric barrier, they're all different kinds of things. And then how fast the plasma propagate is flames propagate a few centimeters or a few meters per second, and they produce probably tens of kilometers per second. So they are similar. And then they break down. It's like ignition, plasma ignition. People call plasma ignition. There are two ways of breakdown. The first is a tungsten mechanism. The second is that streamer mechanism. Lightning is a typical streamer mechanism. And then they have different plasma discharge. I'll show you with a microwave. You have a radio frequency. You have AC and DC, all kinds. But if you're looking at it, it's just that the electron energy are different. Everything and frequency are different. That's only two things. Everything else is the same. Then plasma instability. So what is plasma? So if you're looking at up to the sky, and this is the plasma, right? So this is that the lightning and striking on the ground. You look very bright and skinny. That is because that the plasma break down and create a very high temperature. The conductivity very high. The whole plasma shrink to a very small channel, and with high current. So plasma basically says that is a fourth state of the matter, and a partially ionized, quasi-neutral, charged reactive flow. But when I say partially ionized, not 100% of the gas ionized, and only partially, depending on the plasma. When I say quasi-neutral, I think that quasi-neutral is in the main column, okay, not near the electrode. Near the electrode is not quasi-neutral. Quasi-neutral means they are reactive mixtures. So this is just like a combustion process. So if you're looking at it more virtually, you just say, I have a positive ions, I have a negative ions, I have electrons, I have a neutral molecules, just like combustion. So therefore, to define this a cloud of plasma, what do you need? You need a, know what is the electron number density, what is the ion number density, just so you know what is the radical concentration, what is the stable species concentration. You have the neutral species and the excited molecules, because when electrons collide with a molecule, not only they're getting hot, but also that they start to vibrate, and the electrons, the molecules of electrons can be excited. So therefore, the electronically and vibrationally excited molecules. And quasi-neutral depend on where you are. And most of the places are quasi-neutral. So if you're looking at Newton's law, momenta change equal to the force. And in a plasma process, if you look at the electrons, the electron velocity change as a function of time, and the momenta change equal to the force. It's a Coulomb force, charge times the electric field. That's a Coulomb force that accelerates electrons. But at the same time, the electrons, when they accelerate, they collide with molecules. They will be stopped. Electron energy will be lost. So therefore, you have energy loss. This is my momenta, MVE. But the loss rate depends on the collision of electrons with other molecules. So this is the gain. This is the loss. So now the question is, how does electron velocity or energy depend on in this equation? So you only have two important parameters. One, electric field. The other one is collision frequency. So the collision frequency means how many numbers of molecules do you have per unit volume. So therefore, electron energy is a function about electric field normalized by the number density. So the E over N, so we'll use it a lot. So E over N dictate that the electron energy and dictate the plasma chemistry. So all these kinds of today in silicon manufacturing, people are talking about that the energy of ions, not electrons, but it's also a function of this. And in typical plasma, like fluorescence, I'm not sure it's fluorescent, light bulb, so they are electrons. And you have a gas temperature, just like combustion. And you also have the vibrational, because the molecules start to vibrate. And that vibrate is also a function of E over N. And because that the vibration is caused by electron impact, energy transfer, and the collision process. So I hope you understand this. It's very simple, right? So now we try to get it to say, for electron has temperature, normally people using EV. Is one electron accelerated in 1 volt, that electron volt. It's about 11,000 Kelvin, right? So 1 EV electron. Typically, it depends on the temperature. In this kind of arcing, that is about 1 electron volt. It's about 10,000 degrees. And in a fluorescence light bulb here, and maybe fluorescence, maybe not LED, I don't know. So it typically is about, you talk about 5 EV. So 5 EV is a lot of energy, right? People, if you do a molecular beam mass spectroscopy, people using electrons to break down the molecular, ionize it. So electrons has a lot of energy, so that's why they can excite the molecules. They can do the reaction. Typically, combustion cannot do it, right? So that is the something. So then plasma, and there's a terminology, something called non-equilibrium plasma, or something called equilibrium. In combustion, thermodynamically, everywhere is equilibrium, right? Thermodynamically, because you have enough collisions. Otherwise, you won't have combustion. But plasma is different. They can operate at very low pressure. So they may not have enough collisions to establish thermodynamic equilibrium. So if you're looking at a plasma process, this is lightning. Lightning is very bright. It's because that you have a 10 to the 9th collisions in atmospheric pressure. So therefore, the electron temperature quickly be equilibrated with the gas temperature. So therefore, that the electron temperature, vibrational temperature, and the gas temperature are almost the same. But if you make this a process, for example, if you make it a arc is gliding with, you cool it with air from the bottom, you make that column is very cool. If you cool it, that means what happens? It means that the conductivity reduces. and then the electric field will increase. The electron energy will gain. In that case, when electron energy is gained, and so therefore the temperature of electrons is slightly higher than vibration, slightly higher than temperature. So this is called gliding arc. And the temperature, gas temperature, is about 1,000 Kelvin, but the electron temperature can be 20,000 Kelvin. That's a gliding arc. Gliding arc has a lot of applications in chemical processing and remediation of pollutant. And if you want to have more ignition, you can use it in something corona. For example, you have a metal rod, you put a very short pulse, and then you can generate this kind of streamers and flying around and very large volume. In this case, because the pulse time is very short, imagine the pulse is comparable to a few nanoseconds, then you don't have time to equilibrate the process because the collision doesn't have enough. So you have an electron temperature much, much higher than vibration, much, much higher than T. So most of today's research focus on here. They drive that electron temperature very high so that they can do some chemistry people do. For example, for CO2 dissociation, people want to do this electron temperature very high. So go into this direction, you are going into non-equilibrium, and go into that direction, you are going to equilibrium. But once you go to non-equilibrium, that means that the temperature is going down. If the temperature is going down, that is the electron number density is lower. Electron temperature is high, but electron number density is lower. In this way, if you go to hot, you get more ionization, the electron number density is high. So in plasma, in principle, what people are doing is people to control two things. One, electron and vibrational energy. Second, electron number density. So that can tune that the chemistry in the plasma, right? Just in combustion, what do we do? Control the temperature, control the radicals, right? So that's are the two things we control chain branching process in combustion. Is that clear? All right, so next. So if we're looking at a plasma process, in a plasma, so you have ions, positive, you have electrons, you have electric field. The electron is very light. Under the electric field, the electrons will be accelerated very quickly, and ions move slowly. And so when electrons gain energy, and they can become hot because they have energy. When the hot electrons collide with a molecule, and they form ionize it, they strip one electron away, and then make an ion and make another new electrons. So, and sometimes the electrons collide with the molecule. They don't ionize, but they excite the molecules. And so that, for example, oxygen, it can be excited, and that excited state, and then you can vibrationally excited state. So you can see they have ions, electrons, excited states electronically, excited state vibrationally. So these processes are very fast. They're fast at one electron collision. What does it mean? One electron collision is less than 1 nanosecond. It will happen, right? So, but once they form electronic excited energy, electronic excited, they collide with for example, oxygen. They dissociate oxygen into 2 atoms. But what is the extra energy goal? It becomes hot. Heat, right? The energy is more than to dissociate 2 oxygen to form 2 atoms. Then you generate this process they call a fast heating. So that process only takes about a few 100 nanoseconds to get dissociated radicals, but it generates heat. So this heat is very fast. After that, vibrational excitation, vibrational molecules now start to collide with neutral gas. They give the energy to the neutral gas. But the vibrational energy, it takes thousands of collisions to give the energy back to rotation and translation because the energy is different, right? So that process, so if this process is fast, and then the plasma becomes thermalized, hot. This process is slower compared to the vibrational excitation process. The process becomes a non-equilibrium. Is that clear? For example, in a flames, in a reaction zone, you will find that the radicals concentration is very high because the radical production is faster than the recombination. But after the flame front, you reach equilibrium, right? So it's just like similar. Non-equilibrium just like in the reaction zone. And then equilibrium just like after the exhaust burning gas. Is that clear? All right. So now, well, the next thing we want to see that is the energy distribution function, because we want to study electron impact reactions. So you want to see what is that energy distribution. For combustion and equilibrium, your energy distribution in terms of velocity is following that Maxwellian distribution, is a exponential function, and it's like this. But in a plasma, they don't follow that Maxwellian distribution. They have very high energy tail, that these are the electrons, because they are not equilibrium. They have very high energy there. This thing, control this, is going to be great to control the reaction, because they have some of the molecules very high energy compared to this. And to do that, because they are not a Boltzmann distribution, and you have to solve this Boltzmann equation. That is the change of distribution function compared to the transport and then the external forces and collisional energy transfer. So this is so non-Boltzmann distribution and the Boltzmann equation solver that are the important to solve non-equilibrium plasma, right? So it's slightly different from combustion process. So I try to show you something here. If you're looking at a plasma, they call energy transfer in plasma. So if you fire electrons, this is that the electron energy, E over N. Everybody understands. The unit is tonsant. So if you have a very low electron energy, so you can see that the vibrational oxygen, vibrational nitrogen, vibrational methane, they will be excited. If you have high electron energy, that the oxygen will start to dissociate at around 100 tonsant, and then nitrogen will be excited, and then nitrogen will be dissociated, will be ionized, and methane will be. If you look at this diagram, they give you a hint. Hint what? If I want to control the chemistry of combustion chemistry using vibrationally excited, I want using very low electron energy. I want to generate radicals, I want using high electron energy to generate radicals. So they give you additional knob so that you can tune combustion chemistry or reaction chemistry. And also they can, because it's non-equilibrium, you can pump that vibrational energy higher and higher than that of the Boltzmann distribution. So the key question in the plasma is that how can this non-equilibrium excitation, vibrational, electronic, and they can control chemistry, right? And so if you're looking at, just try to give you an example. If you're looking at this picture, this is the time, this is at the temperature, and this is the plasma. Once you have a discharge, you can see this is the, by the way, this is at the Yiguang and Walter Lampert, Ohio State. They measure this. So you can see the vibrational energy. This is the tens of nanosecond. The vibrational energy of nitrogen is exciting, and this is by electron collision process. And here that is exciting again. This is by excited molecule, electronically excited molecules. And then they decrease and give the energy to rotation temperature. If you look at the rotational temperature, it's fast heating, and they have a slow heating. This slow heating is vibrational energy give it to rotational energy. So it's very clear this kind of a non-equilibrium process, right? Fascinating, isn't it? Yeah. So, and you can measure it, and you can compare to the model about that gas temperature, vibration temperature, and electronic excited nitrogen. You can start to see how that the plasma electronic excited, vibration excited temperature, they dictated the process, right? So these, then the more important, this is all the research of plasma. And when I come to this field, I look at this, these are plasma people are working on it, but how does that impact combustion? So I wrote a proposal to Air Force. I say, I want to study that how this kind of vibration and how that the species, electronic and excited, they affect the combustion process. That's the first research grant I received in 2005. And now it's about 20 years, and that area growing not only combustion to many other areas. So plasmas. So here that is the electrode, and this is the plasma in the flames. And you have different plasmas. They call DC, it's direct current, depending on what is that the current you apply. You can have AC and the alternating current, and you can have radio frequency. It typically tens to hundreds megahertz. And why do you want to change frequency? Any question? Why do you want to change frequency? What? Change the rotation of electrons and go into different ways, right? And and also change that the coupling between electrons with plasma. I will tell you later. Frequency matters. And you have microwave. Everybody is familiar with microwave, gigahertz, and then you have pulse. It can be nanosecond, it can be picosecond pulse. There are different kind of. This is when people are talking about this, they're talking about frequency. And also you talk about temperature. You call non-thermal and you call thermal. This is just what I said. It's a non-equilibrium or equals equilibrium. This is arc, for example. This is at the fluorescence light bulb, for example. And typically that's non-thermal means the temperature is very low. It's a room temperature to a couple thousand Kelvin. And then thermal normally is several thousand to tens of thousands. And then non-thermal means that the electron temperature is very high. And the thermal means that everything is equal. And for example, you have RF, radio frequency discharge, glow discharge. They are non-thermal. This is arc, like lightning and arc, the arc jet, they're all thermal. And also the people to say discharge process. Sometimes they call streamers. Sometimes they call corona, glow, arc, nanosecond. That's all depend on the people call it. And some of you may not understand it, and we'll show you example what it is. And the discharge type, sometimes they call electron beam and all kinds of surface discharge and gliding things depend on the motion of the plasmas. So here I show you an example. What is plasma? Combustion is typically a weakly, very weakly ionized plasma because people put an ion probe into the flames, you can collect the current, right? So they have very weakly ionization. The electron number density is very low. So this is a glow discharge. You can see that, and this is that the lightning is the arc, and this is the laser is a plasma. This is at the sprite in space, and the corona discharge, and this is a nanosecond dielectric barrier discharge. It generates very uniform discharge with a big volume. So how plasma is different? Well, they're different by, as I said, by electron temperature and by electron number density, right? So flames is here, very low electron temperature, very low electron number density. But you have to look at the corona, nanosecond discharge, dielectric barrier discharge, and they have very high electron temperatures. And so these map allow you to control about the reaction process. And so I try to give you an example. This is a table, and very busy, and given by Yiguang at the Princeton Plasma Physics Laboratory. It's too busy, I'll show you three things. Atmospheric pressure arc. This is arc, certainly is equilibrium plasma. You can see that the temperature is about 1 electron volt, 10,000 degrees, as I said before. And then that the electron number density is 10 to the 22 per cubic meters, very high concentration, almost. And then ionization rate is 100% to 1,000% about ionization rate of molecules. And then you look at the nanosecond direct barrier discharge. That's what I do normally. You see the electron temperature actually is 5 eV or even higher, tens of eV. And then you have the temperature is a really room temperature. Ionization rate is very low, 1 ppm. Just like combustion in the radicals. Many times the combustion in the radicals, the low temperature flames, the combustion, the OH radical is about 1 ppm level, right? High temperature flame, radical level is what? Hundreds of ppm, right? If you look at the arc, it's hundreds of ppm, something like that. Same thing. And you're looking at this Hall thrusters today that you see SpaceX. SpaceX launched a lot of Starlink. The Starlink using Hall thrusters, and there, that electron temperature is hundreds of eV. And so the ionization rate is very high because they're using this kind of a Hall throttling process. So these are just to give you examples of plasma. And then I try to go to you, what are the applications? So if you're looking at the plasma, The plasma has two different forms. One is volumetric, large volume. One is contracted to small volume. So for ignition, you want to contract it. You got a lot of hot things to ignite. But for chemical manufacturing, you want a big volume because you want to process a lot of things and in a bigger volume. The question is that how do we control it? This is a instability. It's similar to combustion. I'll show you how. And plasma also has a lot of chemistry because they have electrons, they have excited states, they have this kind of radical production at a very low temperature. So you can ignite it, advanced engines at lower temperature, for example, HCCI. You can do a dry reforming of CO2 and methane into ethylene. Or you can do a pollutant control and to remove this aromatics by generating this kind of OH and O and a singlet oxygen ozone process. You can make nanomaterials in a non-equilibrium form. So that gives you a lot of a variety of applications of plasmas. And then in combustion field, particularly that is the Raman scramjet engine detonation, that is a very fast process. And detonation and scramjet engine mostly are dictated by ignition process. If there's an ignition become a problem, the first thing you should think about plasma, because plasma control ignition is like a magic, okay? That's why internal combustion engines all have a spark plug, see what I'm saying? Because they control ignition so fast. And you can also control, for example, a mild combustion when the exothemicity is lower. You can develop a cool flames. I will show you that how plasma can easily stabilize the cool flames, and how you do the fuel reforming, control emissions, develop new engine technology. So that is a lot of applications because of this plasma process. But if we really want to understand plasma, we have to go too deep about the governing equations, just like the flames, right? So plasma is governed is electromagnetic wave. They subjected to Maxwellian equations, like that electric field, magnetic field. And then these are the equations here. B is magnetic field. The rho here is that the net space charge density, and J is the current. If you take that the current, writing in ion motion versus electron motion, and in using the velocity like a mean velocity versus a relative velocity, and you substitute into this, you can say my current density equal to that space charge mean velocity motion plus a diffusion between ion and electrons. This is exactly the same in combustion, that you have a mean velocity, you have a diffusion process. And if you note that the rotation at divergence becomes 0, and then you can write down, combine these equations, this one and that one, you can write down that the space charge change as the divergency of current equals 0. This is like continuity equation of combustion, isn't it? Density change equal to the velocity divergence. So this is that what you have. People model plasma using these equations and then Maxwellian equations. But in many cases in plasma, we are dealing with that the magnetic field is negligible. If this one is negligible, and then the E rotation will be 0. If E rotation is 0, they can write E as a function of gradient. So E must be a function of a gradient. So if you substitute this one into this equation, you get a Poisson equation of potential that equal to that rho is a space charge divided by a permittivity. So this equation called Poisson equation. So in many plasma, you need to solve a Poisson equation to find that the voltage distribution and electric field distribution, and then using the electric field distribution to calculate E over N so that you can calculate electron temperature. So in one-dimensional case, this equation reduced to electric field gradient equal to this, and then the voltage distribution equal to this. It becomes very simple. And sometimes you have analytical solutions for these equations. So these are used to solve electric field, and then So for diffusion, you can see that ion diffusion is that the diffusion flux equals to the number density of ion times the diffusion velocity. That equals to mobility of the ions due to electric field plus a diffusion. The same thing you can write down for electrons that equal to the diffusion process plus that is the mobility of electrons. But when plasma becomes quasi-neutral, the flux of positive and negative ions has to be equal, right? Otherwise, it won't be equal. So therefore, you put this thing the equal, and then you put this one equal, you can calculate this electric field. This electric field is built due to diffusion process. When electrons move to one side and ion move to the other side, and the diffusion rate are different, then the number density will be slightly different. You build this internal electric field. And you substitute this thing back to the equation, you can derive that the diffusion of ion and electrons is proportional to that the number density multiplied by diffusivity. This diffusivity we call ambipolar diffusivity. It's not just the diffusivity of thermal, it's because that diffusion is constrained by the internal electric field, because electrons cannot diffuse too far away from ions. Ions will attract you back. So this is called ambipolar diffusion. So if you put this one into it, you will see ambipolar diffusion is proportional to the electron diffusivity, ion diffusivity, divided by mobility of electrons and ions. The ions is very heavy, so therefore mobility is very small. You can ignore it. So ambipolar diffusivity becomes to diffusivity of ions times that the ratio of temperature. Remember, electron temperature is 10 times or 100 times higher than ion temperature. So therefore, that the diffusivity of ions and in plasma is order of magnitude higher than the thermal diffusivity you calculate by using chemicane, right? Using chemicane to calculate that the diffusion of ions is wrong. You cannot use it. Or you have to use it in this ambipolar diffusivity. And so the next thing I try to talk about, what is that break time? What, in 10 minutes? Is it 1 hour or is it what? 9:45. Okay, so, all right, great. So we have a plasma, just like combustion. Combustion has a length scales, for example, flame thickness and diffusion thickness. And then plasma here have a mean-free path, because how fast the electron can free transport without collision. The plasma also has a Debye length. And in that length, plasma is a highly, charge is not equilibrium. And outside the length, plasma is neutral. And within the length, plasma is not neutral. And you can, this should be skin depth of plasma, how fast. If you have a plasma, you put the electric field, how deep that plasma can penetrate. We call skin depth. Time scales, plasma frequency, charge polarization frequency. There are different time scales, just like ignition, you have a thermalization in plasma, in combustion process. Mean-free path, everybody in this class understands. When you have a molecule travel with a velocity of u and in a particle, and then you will travel a certain distance on lambda, and before you collide with a molecule. So the mean-free path is basically that is the traveling distance per unit time and divided by a number of collisions per unit time. So the travel distance per unit time is velocity, and the number of collisions per unit time is that the cross-section area times the velocity times the number density. So this is that the mean-free path. So mean-free path is the inverse of a number density. That's why the E over N come, because the mean-free path is that the inverse of number density. And if in air, that is 300 Kelvin at the atmospheric pressure, the molecule diameter, for example, is 3.5 angstrom. You calculate the mean-free path is about less than 0.1 micron. Less than 0.1 micron is the mean-free path in atmospheric pressure. So that's why the plasma in atmospheric pressure is always unstable, contracting, because there are too much collisions to thermalize it. But if you have electrons, and the electrons will be different. And so if you have electrons, electron mean free path, because electron velocity is much higher than the gas velocity. So this is at the electron mean free path. Typically, that at 1 atmosphere pressure, the air is electron mean free path is about 5 microns. It's order magnitude longer than, because electron diameters is small, and at the same time that it traveling much faster. So this is at the collision frequency of electrons. This collision frequency dictates the reaction rate in combustion kinetics, chemically. You have to say, okay, 10 to the positive 9, or many of them is because of the collision, right? Not every collision will cause a reaction, of course. So other important things is that the Debye shielding in a plasma. In a plasma, imagine you have ions here. If you put a charge into the plasma, what happens? Positive charge, then electrons will move towards you, and the positive ions will be repulsed, going away. So you form a sphere within a length of Debye that the number density of positive and negative, they are different. Outside, there's no effect at all. The electric field is 0. So this is that they call a Debye shielding length. Outside is this, nothing. And inside of this is highly in non-equilibrium. So that, for example, if we have a plasma, this is a gliding arc. It's an arc gliding around the electrode. This is the cathode. This is the anode. You start to see in this column, they're all outside of this Debye length. So they are positive and negative combinations. They're all equilibrium. And near that the cathode, for example, the electrons coming out and accelerate very fast. Not many electrons in this. But there are a lot of ions that move slowly coming here. Here you have a lot of positive ions, a small number of electrons. And here they are neutral. So here you have very strong electric field. This is why you see very bright, because the electric field is strong, then electron energy will be high, and then you generate a lot of chemistry around here. The same is an anode. This bright spot, it is that the shits of Debye length. Is that clear? All right. So how large is the Debye length then? So you start from this Poisson equation. Divergence of electric field equal to space charge. And using electric field is a gradient of, if you assume magnetic field does not matter. So you write down the Poisson equations. This is voltage, this is the charge. Then you normalize this equation, both sides. You divide it by the number density of ions, and then and the temperature. So you normalize this potential using electron charge with the temperature and this both sides. Then this equation is normalized both sides. Then you find that the dimensionality and in the button, that is the Debye length. So you just simply by normalize that equation, and you can define what Debye length is. So therefore, if you put that the temperature, electron temperature is 1,000 Kelvin, for example, the number density is 10 to the 13th, maybe 1 ppm, and the Debye length you calculate is about almost the same as the mean free path of air. But it's dependent on electron temperature, depending on electron number density now. So there are many things here. So therefore, that when the length scale is larger than this Debye length, and then everywhere is quasi-neutral. So the condition is that within this sphere of the Debye length, that electron multiplied by electron number density, you have enough electrons to shield away of that the charge impact. All right, so we now understand Debye length. Then what is that the distribution of potential? So to understand that, and we understand this, again, this is the Poisson equation, becomes to the space charge. Let's say they look at here. So let's say we put 1 electron in the center and see how the potential will decrease. So the boundary condition is that at phi field, there's no voltage. And in the center, you put 1 electron there, they create a potential on the center. Using this as a boundary condition to this equation, and using a Boltzmann distribution, here you can say the electron number density is proportional to that the exponential function. This is that the negative potential, and for the ions is a positive potential. So you subtract this, you calculate the delta n. You find the delta n just equal to this. And you substitute this to that equation. You're looking for a spherical coordinate with this is space charge. Here you can find the solution is exponentially function. So the potential in a double lens is exponentially decreasing. And that the radius of the double lens is proportional to that the product of electron temperature, ion temperature, and normalized by the charge density. And typically, for non-equilibrium plasma, you just write down the double lens is this, which is same form as we developed using simple non-dimensional analysis. All right, so now we learned that the double lens, and we learned that the potential distribution. So the next thing we want to learn, plasma frequency. Why do we worry about plasma frequency? Well, when you have a plasma doing something, and you put the electric field, you want to understand how that electric field will change the plasma. Sometimes the plasma is stubborn. They say, OK, I have no change. And sometimes the plasma is OK. They respond to your electric field. So that depends on the plasma frequency. For example, if we have a neutral plasma, and you shift the positive and negative charge to one position, so then you create a total charge is that the electron charge times the number density times that the volume. And then the electric field will be the charge divided by a permittivity divided by the surface area. This is that electric field. Then the Coulomb force will be that equal to the charge times the electric field. And this is that permittivity. Once you have a force, you can use a Newton equation to say my acceleration of electrons equal to this force due to that charge motion. And this is a very easy equation. You can quickly find that the oscillation frequency is the square root of this. And if you're using that the number density per cubic centimeter, this is what it is. For example, if the electron number density is 10 to the 9 per cubic centimeters, and then the plasma frequency is 300 megahertz. So that means plasma can respond at 300 megahertz. But of course, it depends on the number density. The high electron number density is easy to respond. Now, for example, if you have a microwave, you put milk into it, that plasma basically penetrated your glass, right? The heat is very uniform, right? So don't do it. And in case that you put a metal inside of the microwave, what happens? You see a lot of arc on the surface of the metal, right? Because the electron number density in the metal is very high. What does it mean? If this one is very high, what does it mean? The plasma frequency is very high. They can respond, right? Even microwave is 2 gigahertz, but this thing could be higher than 2 gigahertz. So when the electric field come in, the electrons, they try to respond. And then you reflect your energy away. See what I'm saying? You generate a spark, right? The electric field, the reflection, very strong. Just like tennis. You put a tennis ball to the wall, and the ball reflects back. And you feel a very strong electric field on the surface. So this plasma frequency is very important. If that your electric field wave number is smaller than the plasma frequency, and the plasma will respond and extract energy from the electric field and reflect that incident wave away. This is what happens when you put a metal in the microwave. On the other hand, if the plasma frequency, the electric field frequency is larger than that, the plasma frequency, and then that the plasma can transmit through it with no reflection. So if you heat a milk in the microwave, because the electron number density is very low, So the WP, the plasma frequency is very low. So what happens? Electromagnetic wave is 2.4 gigahertz, it just penetrating, right? So that is why that the microwave make it so good that they can do a plasma manufacturing at a atmospheric pressure, which have higher electron number density because that the electric field is very strong. So therefore, there you have a critical plasma electron number density at which that the plasma can switch from reflective mode to transmit mode, right? So that is the key to design whether plasma can work at which pressure, at what electron number density. So just try to be a schematic for if you have a low electron density, then your plasma frequency is lower, and then the plasma will transmit it, okay, with some decay, of course. And all the electrons here acting like a collective particles. They move together. And if that the electron number density is very high, like a metal, you have high plasma frequency, and then electric field frequency is smaller than this, then plasma will be reflected. You generate a discharge and spark on the surface. So this is that individual particles. Each individual, they can respond by itself. So this is like so now that the second thing that is the polarization and of charges. So if you have a charge and you have a current, the question is how fast the plasma can respond to a charge motion. So this is that the continuity equation. This is that by definition about the current, and this is that the Poisson equation. You substitute this into here and substitute this into there, you can find a solution about how charge, space charge, is going to change as a function of time. So you find a solution that this tau is at the polarization time scale is proportional to the permittivity normalized by the conductivity. So this motion is different from the plasma frequency because this is that the collective, that the motion about electrons or charge, space charge, in response to electric field or current. So it's that the space charge motion is not that the plasma electrons motion by itself. So for example, if you have nitrogen with 100 tau, electron number density 10 to the 10, and the temperature is 1 eV, and that the polarization time is 12 nanoseconds, which is far longer than the time scale about the plasma oscillation frequency defined. All right, so, and then it also has a plasma skin depth. When you have an electric field interacting with the plasma, this is that the skin depth, how plasma can penetrate. If you solve the Maxwell equation, that the depth of skin and is proportional to the mobility and the frequency of electric field and then conductivity. So if we assume this term are small, for example, electron number density is high, and then we can say the skin depth is proportional to square root about conductivity and omega, and proportional to the inverse of plasma frequency. And so these are the things you don't need to remember. Just want to see that there's some length scale there, and you need to understand when you deal with plasma. Okay, let's take a break, and then again, then we can move to the next session. All right, so for 15 minutes.